Hi everyone, in this video we are going to look at 10 practice problems on the topic electric flux and Gauss law, and these 10 problems would be ranging from easy to hard. So I'll cover all types of questions, easy questions covered in CBSE, medium questions covered in mains, or even the hard questions covered in advanced. So let's jump right into it. So firstly, this is a question. So we are given a hemisphere, a hemispherical body, a solid hemispherical body, and we are given a uniform electric field E. The radius of hemisphere is R, and the question is that we have to find the net flux through the hemisphere. So this is a very easy question. So whenever there is a uniform electric field, net flux through any closed body, any closed surface, is always zero. So there are two ways to visualize this. First, you can think of this as like number of field lines that are entering into the closed surface are equal to the number of field lines that are exiting from the closed surface. So since flux is nothing but number of field lines passing through the surface, so the negative and positive flux balances and it becomes zero. Otherwise, also as we discussed in the last video, in uniform electric field what happens is, so since when the field lines are entering, the points where field lines is entering, the flux is negative, and the points where field lines are leaving, the flux is positive. So with uniform electric field what happens is that the sum of the positive and negative flux balances out and net flux becomes zero. So that's why whenever there is a uniform electric field and a closed surface, net flux is zero. However, if the electric field is not uniform, is not same at every point on the closed surface, then the total flux, net flux might not be zero, and we have to calculate in that case. Now to make this more interesting, the second part is find the flux through the curved surface. So we have to find the flux through this surface. Firstly, we can note that the flux through this surface would be positive, since the area vector at any point, let's say this is area vector at this point, makes an acute angle with the electric field line. So here this is area vector, this is electric field line, here this is area vector, this electric field line. So at every point on this curved surface, the area vector and electric field lines would make an acute angle, hence the flux through this curved surface would be positive. And flux through this flat surface here, this surface, so basically flux through this flat surface would be negative, because area vector would be in the left direction and electric field would be in the right direction, so angle would be obtuse. So basically in this case the angle is 180 degree, so flux would be area into E into cos of 180, which is minus E. So we know that the flux through the curved surface plus flux through flat surface is this surface of the hemisphere, is zero, because net flux is zero, and we know that flux through flat surface is negative, which is equal to area of the flat surface. Since we are given radius to be r, so area of flat surface is pi r square into the magnitude of electric field. At every point on the surface, the magnitude of electric field is same because it's a uniform electric field. So we'll just multiply it by E and we'll add a minus sign because area through flux through flat surface is negative, and flux through curved plus this should be zero. So simply flux through curved surface is equal to pi r square E, which is positive. So this was also pretty straightforward. So now let's move to the next question. So this is the case, and this question has been sometimes asked in even CBSE exams. So this is also not very difficult, but the only difference with the previous question is that in this case the electric field is not uniform. So electric field depends on, so let's first see this case. So electric field depends on value x. X means the point, the x coordinate of the point. So here x coordinate of the point is 0. So for all this plane which I am shading, for this place x coordinate of the point is 0, and for this plane which now I am shading here, the x coordinate of the point is a, because we are given a cube of side A. and for in between points, for example, for maybe some plane in between here, for all these points the x coordinate would be a by 2 and so on. So since electric field only depends on the x coordinate, we can see that for this surface, electric field is uniform at every point on the surface, which would be equal to I cap, means the electric field is in the direction of x-axis, which is towards the right in our diagram. So at every point here, the electric field would be 2a at every point on the surface. So here it would also be 2a. So here it would also be 2a. And the area vector for this surface would have direction towards the right as well. So the flux through this surface, let me say this is surface 1. So flux through surface 1 is a into e cos theta. Since angle between a and e is 0, so it would be a e cos 0, and the value of area is a square, and cos 0, the value of electric field is 2 times a, and cos 0 is 1. So basically flux is 2a cube, and it would be positive flux. Now similarly, through this side, at every point on this plane, the electric field is same. And how much is electric field? Electric field is 2x I cap. Since x is 0 for every point on this plane, x coordinate is 0, so electric field at this at every point would be 2 into 0, which is basically 0. So since so let me call this plane as second plane. So electric A dot E, which will be equal to AE. Now area vector would be left side toward this, for this surface, towards the left side, towards the negative x-axis, AE cos 180, and this would be equal to 0 because E is 0. So now we have calculated flux to surface 1 and 2, and there are 4 more surfaces. We do not need to calculate flux through surface 3, 4, 5 and 6. Reason is the flux through those surfaces is 0, because the area vector would be perpendicular to the electric field vector. Electric field vector is along the x-axis. But here the area vector would be along, let's say for this surface, for the front surface here, the area vector would be along the z-axis. Z-axis is perpendicular to x-axis, so area vector would be along the z-axis. So this would be basically 90-degree angle, and AE cos 90 is 0. Basically, for the planes for which the electric field lines are parallel to these planes, that's why flux through the planes 3, 4, 5, 6 is 0. So net flux through this cube would be simply phi is equal to phi 1 plus phi 2 plus phi 3 plus phi 4 plus phi 5 plus phi 6, which would be simply equal to phi 1 because everything else is 0, which would be equal to 2a cube. So this is the final answer, and net flux would be positive. So a similar question, just a like slight variant of this, is this question. So here we are not given 2x I cap, we are given just a constant c. We are not given the constant, you can assume any constant, and we have to find the net flux to this cube here. Now this cube is at a distance of 2a from the origin. So only difference between previous question and this question is that, so again for the surfaces, only for the surfaces this surface and this surface would be flux non-zero. For all other surfaces flux would be 0 because those surfaces are parallel to the electric field lines. So for every point on this surface, flux is constant, and it is c times the x coordinate, which is 2a, and it is in the right direction. Similarly, for every point on this plane, the electric field is also constant, and it would be equals to c times the x coordinate, which is a, and it would be in the right direction. For this, the area vector is in right direction. For this plane, the area vector is in the left direction. So area vector is basically normal and perpendicular outside the surface. So flux to surface 1 would be, now it should be very easy, c times 2a, which is the electric field into area, a squared. So this would be 2a cube c, and it would be positive since a and c are in same direction, and cos 0 is 1. Flux to second surface would be c times a squared, and it would be negative since cos 180 is minus 1, or you can say that area vector and e are in opposite direction. So this would be simply ca cube. So net flux is phi 1 plus phi 2, which will be equal to simply A cube C. So the second part is find the net charge inside the cube. This is very straightforward. So we know that the net charge enclosed by epsilon naught is equal to flux through a closed body by Gauss law, and we have already calculated the flux, so we can find Q enclosed. So Q enclosed is nothing but A cube C epsilon naught. So let's move to the next question. So this is an interesting question. You have to find the flux through one side of a square, which can be any side because it's a symmetrical situation. So there is, so let me first explain the question. There is, you are given a cube of side A, and you are given a charge Q which is placed at the center of the cube. So net flux passing through this cube by Gauss law should be Q by epsilon naught. Now because it's symmetry, so imagine that you have to find like how many field lines are passing through each of the surface. So imagine that it's a sphere. Like field lines for a point charge is like a sphere. Equally, field lines are going equally in every direction in form of a sphere inside this cube. And for every surface on the cube, the area vector and the electric field line would make acute angle. So for every surface on the cube, the flux would be positive, and it would also be equal because from every side of the cube, equal number of field lines would be passing. So by using the symmetry, we can say that, like, let's say we pick this top side of the square. So since for every side equal amount of field lines are passing, so and total flux passing through all the sides is Q by epsilon naught. Therefore flux passing through one side is simply Q by 6 epsilon naught because we have 6 sides. So this was also pretty straightforward. Let's move to the next question. So this is one of the questions which also sometimes comes in CBSE to derive the electric field, and it's better that you learn or remember the result of this question. So first let me explain the question. The question is that electric field due to a uniformly charged sphere, and keep in mind that it is an insulating sphere. So there are two kinds of spheres, conducting sphere and insulating sphere, and properties of the two kind of spheres or two kind of material, not just spheres, it can be for any material, either insulating material or a conducting material. The properties of those two kind of material are very different. So please, when you are reading the question, take care that what kind of material are you given. Is it insulating or is it conducting? So we are given a insulating sphere, and it's a uniformly charged sphere. What do you mean by uniformly charged? Basically, at every point inside the sphere, the charge density is, so the sphere is filled with positive charges. Let's assume the sphere is filled with positive charges all equally everywhere. So you take any volume of this sphere, let's say 1 meter cube, take 1 meter cube area, 1 meter cube volume of this sphere anywhere inside this sphere, anywhere. Let's say we take 1 meter cube here. So this is 1 meter cube volume. So amount of charge in this 1 meter cube is given to be rho. Rho means the amount of charge per unit volume. Charge per unit volume. So charge is coulomb per meter cube. So that's called a uniformly charged sphere. Basically, the charge is filled inside the sphere uniformly at every. If you pick 1 meter cube here also you will find the amount of charge inside this volume is rho. So that's why it's called uniform. At every 1 meter cube volume, the charge inside the sphere is rho. So now you have to find electric field due to this sphere at point somewhere inside the sphere and at a point somewhere outside the sphere. And let's say we are given, so it is given that the radius of the sphere is capital R. So this is given. So if radius of the sphere is capital R, now we have to find that how much charge is enclosed inside this sphere. So what we'll do, let's say that, so now we have to find the electric field at a point R from the center such that that point is inside the sphere. So we can take any random point, let's pick this point, and this point is at a distance R from the origin. We have to find the electric field at this point, and to find the electric field we'll construct a an imaginary sphere passing through this point like this. And at every point of this imaginary sphere, the electric field would be same. At every point of this imaginary sphere, electric field would be same. And electric field can be derived from Gauss law, which is the net charge inside this imaginary sphere at distance r, which is less than r, by epsilon naught should be equal to the flux. And flux is nothing but, since for this imaginary sphere the area vector and electric field vector would be in the same direction, flux would be simply area of the sphere, surface area of the imaginary sphere multiplied by the electric field. And this is what we have to find. So this will give us value of E. So we know the surface area is nothing but, so for a sphere the surface area is 4 pi r square. E we have to find, and we can find the charge, right? Q inside this sphere is nothing but charge per unit volume into volume of this imaginary sphere, which is 4 by 3 pi r cube. So charge enclosed is rho into 4 by 3 pi r cube divided by epsilon naught. So this will give us the value of E. E should be equal to, so this will cancel, only one power of r remain, so it's nothing but rho r by 3 epsilon naught. So if r is less than r, the electric field at that point is rho r by 3 epsilon naught. And let's say you are not given rho, you are given instead charge, the net charge inside this, which is like the net charge which is present inside this sphere. Let's say that's capital Q. Then rho can be easily found using rho is equal to Q upon, so rho is basically charge per unit volume. So total charge is Q and it's uniformly distributed for every volume, so rho can be simply calculated by this if rho is not given, instead Q is given. So that's something a trivial point. Now let's do the same exercise for a point outside the sphere at radius r. Let's say that point is this one. So again, for this point, what we'll do is we will construct an imaginary sphere passing through this point. So the steps are same. So we'll use Gauss law. So I'm going to do it very fastly. So Gauss law is flux is equal to Q enclosed by epsilon naught. So flux would be electric field at this point into area of this larger square, which is 4 pi r square, the surface area. Q enclosed would be, now the charge we have to take is the charge enclosed, and charge enclosed would be equal to the charge in this area, the charge of the complete sphere, which is capital Q, and in terms of density it's rho into volume of this. So the radius is capital R, so volume is 4 by 3 pi r cube, capital R cube by epsilon naught. So electric field is simply, this cancels out. So electric field is simply rho r cube by 3 epsilon naught r square. So now we can also construct a graph between electric field and distance r from the center. So let me keep this. So we can see that the graph will have two parts, for r less than r and for r greater than r. So on the x-axis we are taking the distance. So for r less than r, so it's just a y is equal to cx line, which is a straight line passing through origin. Rho by 3 epsilon naught is the constant, x is basically your r and y is basically your e, so electric field on the y-axis. So this would be a straight line passing through the origin, which is like this. At exactly r, what's the value of electric field? We can find by putting r in any of the either in this or in this. because it's a continuous graph. So it's rho r by 3 epsilon naught. And after that, if we increase r further, then your electric field decreases because r is in the denominator. So if you increase r, electric field would decrease. So initially it increases linearly and then it decreases like this. So sometimes you have to draw this graph in your CBSE exams. So you should know this. So let's quickly move to the next question. So as I told, there are two kinds of spheres, either a conducting or an insulating. And now the second question is, you are given a conducting sphere. So there is a property of the conducting sphere that you have to remember, and the property is that there can be no field inside any conducting material. So this is a necessary property. There can be no field inside any conducting material. So let's say again we are given a sphere, but this time it is made up of some conducting material. Let's say it is made up of metal. So since metal is conducting, and again let's say we are given that the total charge on this conducting sphere. So firstly, radius of this conducting sphere is r, and total charge on this conducting sphere is q. Is q. So as I said that there can't be any, since this is made up of metal. So for this sphere, imagine a metallic ball. Since this is conducting, there cannot be any electric field inside this. So if we take any point r inside this, the electric field at this point should be 0. So electric field at this point should be 0. So for r less than r, electric field is 0. This is by the property. But one thing to note is electric field at this point can only be 0 if charge enclosed is 0, because E into 4 pi r square is equal to Q enclosed by epsilon naught. If we apply Gauss law to this blue sphere, imaginary blue sphere, but we know that E is 0 by the property. Therefore, Q should be also 0, which means that for any point inside this sphere, the charge is 0. So charge cannot lie inside this sphere. So all the Q charge would be at the boundary of this sphere. It can't be inside, it would be at the boundary of this sphere. So basically charge would uniformly distribute itself at the boundary of this sphere, and instead of using the terminology of charge per unit volume, because charge is only on the boundary, we will use charge per unit area. So area of this sphere is 4 pi r square. This is charge per unit area. So for any point inside the sphere, the charge at that point would be 0, and electric field at that point would also be 0. Now for any point outside the sphere, let's say we take again an imaginary point here outside the sphere R. We'll create an imaginary sphere to apply Gauss law. Net flux to this sphere would be, since area vector is in this direction, electric field would be in this direction, net flux would be E into 4 pi r square, which would be equal to net charge. Net charge, suppose we are given Q by epsilon naught. So this would be simply like Q upon 4 pi epsilon naught r square. So you can see this is the same formula which we get for the point charge. So for any point outside this metallic conducting sphere, the field experienced is just equal to if all the Q charge were concentrated at the center of the sphere. Like if there was a point charge at the center of the sphere, then also the field would be the same. So but that's not important. So the important thing is charge cannot be inside the sphere, and that's an important property that's gonna be used in many of the future questions that we are going to be doing. Now the graph would be something like that. So before R, electric field is 0. So basically graph would be like this. Electric field is 0. And after R, suddenly electric field is Q upon 4 pi. So this point is Q upon 4 pi epsilon naught r square. And then electric field would decrease because small r is in the denominator. So this graph will be something like this, a jump and decrease. So this is one of the derivations that might come in your CBSE exam as well. So a slight different version of the same question, but an interesting version is this, which you can call this question as CBSE or mains level. So you are again given a conducting shell. So instead of sphere, you are given a shell. So basically there was a metallic ball or metallic sphere, but it has a hole inside it of radius a. So the gray color represents the metal, and this is basically hole, and this is air. Basically this is also filled with air inside, like there is no metal, nothing there. And now you have to find the electric field at three kind of possible points are there. Either the point can be inside this cavity, or point can be inside this metal, or point can be outside this metal. So this is easy. If point is inside this metal, this case, you know that if point is inside the metal, there cannot lie any electric field because of the property of conducting body. So this should be 0, right? And for any point here which is inside the cavity, let this point is at distance r. So let's apply Gauss law. So case A, so flux E is equal to E into 4 pi r square is equal to charge enclosed, which is simply Q by epsilon naught, right? So for r less than A, it would be Q upon 4 pi epsilon naught r square. Now for r greater than B, for this point here also we conduct a sphere, a very bad sphere I have constructed. Here also the flux is equal to E into 4 pi r square. Should be net charge inside this sphere is Q, inside this imaginary blue sphere is Q by epsilon naught. So this would also be equal to Q upon 4 pi epsilon naught r square. So now interesting thing to note is that you might think that if we construct an imaginary sphere passing through this point and we apply the same thing, so for B we apply the same thing, let's say this is a distance r, we apply the same thing, E into 4 pi r square, and we can see that the charge inside this is also, you know, Q. So it should be equal to Q by epsilon naught, and again the result should be the same, but this is wrong. So an interesting and important thing which can be asked in mains exam is this, that the property remains. The property is that there can be no electric field lines inside a conducting material. So charge inside this sphere, inside this imaginary sphere in pink color, has to be 0, and for that, to maintain that charge to be equal to 0, the conducting body adjusts its charge in the following way. So if Q charge is at the center, what it will do, let's say it's positive Q charge at the center, what it will do, it will uniformly distribute a negative charge inside this cavity, inside the surface, on the surface of this cavity. So basically it will accumulate a charge on the surface of the cavity which would be equal and opposite to the charge at the center. So it would uniformly distribute this minus Q charge on the surface, and such that now if you construct any imaginary sphere inside this metallic region, the net charge enclosed would be 0. So for B, E would be equal to E into 4 pi r square is equal to 0 by epsilon naught, therefore E would be 0. But since the net charge on the conducting shell has to be Q, it's given that Q, the net charge on the sphere is Q. So what it will do is it will also accumulate a plus Q charge on the outer surface, uniformly distribute a plus Q charge on the outer surface area of the conducting body. So if you see the net charge, if you count the net charge enclosed is, so plus Q charge is, so region 1, region 2, and this is charge 3. So 1 plus 2 plus 3 is still plus Q. So net charge of the sphere remains plus Q, But to maintain that property that the charge inside a conducting sphere has to be 0, it accumulates a negative q charge on this surface. So this is an interesting point to note, and it can be asked in many questions. And now you can see that if you construct an imaginary surface at this point at a distance r from center, the net charge is inside is 1 plus 2 plus 3, which is q. So basically this derivation for the case 3 is correct. So please take some time to understand this. This is a very important and interesting concept. So before moving further, please ensure that you understand this, because next question is based on the similar concept. So now this question is similar to the previous question, and if you followed correctly, you will find this one easy. So this can be called a mains level question. So you have to first find electric field outside the shell at any point r. So first let's see what will happen. So since this is conducting shell, let's say it's made up of some metal, so in that case you have to, and there are 2 point charges placed in 2 cavities. So this is a conducting shell and there are 2 cavities, cavity 1, cavity 2. So there is a qa charge placed here. So since electric field at this point on and at any point on this imaginary sphere has to be 0 by property of the conductor. So if it is confusing, let me paint the conductor with some gray shade, and which is not painted is basically vacuum. So these cavities are vacuum, outside this is vacuum. So since at any point in this conductor should have electric field of 0, which means charge enclosed should be 0 by Gauss law, it will accumulate an equal and opposite charge of minus qa on this surface here. Minus qa charge would be accumulated. Similarly on this surface here, by the same reason, minus qb charge would be accumulated. And since an extra minus charge has been accumulated, to balance that out, a positive charge would be accumulated on the outermost surface. So plus qa and plus qb charge would be uniformly distributed on the outer surface. So first question, let's come to the question 3. So question 3 is find the surface charge density. Sigma means surface charge density, which is charge per unit area for surfaces A, B and C. So for this and this. So for surface A, sigma A is minus qa charge which is accumulated. So charge accumulated per unit area, 4 pi a square. Similarly sigma B is minus qb, 4 pi b square. And sigma R, so net charge included on the accumulated on the outer surface is qa plus qb, and divided by the area of this outer surface, which is 4 pi capital R square. So this is the answer to third part. Now electric field outside the shell. So let's take a point at distance r outside the shell. You have to find the electric field at this point. So you have to find that in this imaginary pink sphere how much charge is enclosed. So by Gauss law, E into 4 pi r square, which is flux, is net charge enclosed. Net charge enclosed is simply qa plus qb. So electric field outside the sphere is qa plus qb by 4 pi r square. So this part is done, this part is done. Electric field inside cavity of radius a. Okay, so electric field at any point at distance r. Let's say here we have to find distance r from the center. So again applying Gauss law for part 2, electric field into 4 pi r square is equal to q enclosed is now qa. So electric field would be qa upon 4 pi r square. So let's move to the next question. 3 more questions to go, and the next 3 questions are gonna be a bit tough because they are a bit advanced level. So let's see this. So here, if you remember that we studied that if we have an infinite wire with charge density lambda, that is charge per unit length, coulomb by meter, then the electric field at distance r was given by lambda upon 2 pi epsilon naught r. So let me show you. Here we derived it using Gauss law for infinite wire. So now this question is not at all easy, and if you don't understand properly, it's fine. This is not usually a mains level question. So now instead of infinite wire, you are given a wire which is extending up to infinity on one side, but which is like fixed, which is not extending to infinity on the other side. So it's still infinite wire, but it's not extending to infinity on the other side. And so for practical purposes, infinity means very long wire from the left side, but on the right side there is an imaginary surface of radius r. Some imaginary surface of radius r. And you have to calculate the net flux passing through the surface. So what we will do is we will first find, so step number 1 is find electric field due to wire at radius x from center. Okay, so we will find, let's say at a radius x, how much electric field, so this is x, how much electric field is at this point. Then we will say that we will construct an imaginary thin, so basically this is a very thin, negligibly thin wire. So let this be dx. So ring of radius x, negligibly thin ring of radius x, and we can assume that on every point of this ring electric field would be same. So the flux through this ring would be, so electric field at every point due to the wire, since this is not an infinite wire on both sides, the electric field have at every point will have two components. So it would be in some direction like this, and it will have two components, Ex and Ey. Since Ey is parallel to the surface of radius r, Ey will not contribute to the flux, only Ex will contribute to the flux. So X component would be contributing to the flux. So the net flux through this circular ring is, the X component into area of this ring. Area of this ring is, so you can flatten this ring out and you can understand that the length of the ring would be circumference, which is 2 pi x, and breadth would be dx. So area would be 2 pi x dx. So area of this ring would be 2 pi x dx. Now this is flux through this ring, and we have to calculate the total flux. Total flux would be flux ring, integrate flux through this ring from x is equal to 0 to x is equal to capital R, and you will get your answer. So the difficult part here, the most difficult part here is to calculate this x component, the x component of electric field due to the wire at a distance of height x or radius x. So let's try to compute that. So there is a wire, this is a wire infinite from this side, and we have this endpoint, and we have to, let's say the height I am taking is y. We have to find what is the x component of electric field at this point y. To calculate that, we'll again have to do some integration. So we'll take a point at a length L, and we'll take a very small section of length, negligible length dl. So the charge, so it will apply an electric force to 1 coulomb charge placed here in some direction like this, but we have to take only the x component. So let me complete this triangle. We have to find this x component. So x component would be, basically if this is theta, then this would be theta, so E cos theta, and E would be equal to k q1 q2 by r square. So K is 1 by 4 pi epsilon naught. Q1 is lambda into dl, charge per unit length into length of this small area, small wire. Q2 is 1 because it is 1 coulomb charge, and R square is y square plus L square by Pythagoras theorem. And E cos theta would be, cos theta in this would be based upon hypotenuse, which is L upon root of L square plus y square. So E cos theta is equal to lambda dl upon 4 pi epsilon naught L square plus D square into cos theta is based upon L upon root of L square plus D square. So this is the x component of electric field by this small area, and we have to integrate this to find the net x component, the total x component of electric field at height y. So basically electric field at height y is equal to this. So to take t to be equal to L square plus D square, so that the denominator becomes t raised to 3 by 2, and then dt would be equal to 2L dl. So thank God I made some space, I was falling short of space. So this is lambda by 4 pi epsilon naught. So L square plus D square, we have a power of 3 by 2, so t have a power of 3 by 2, and then L dl is equal to dt by 2, and then we integrate. So when basically we were integrating this for L is equal to 0 to L is equal to infinity. So when L is 0, t is equal to d square, and when L is infinity, t is infinity. So this would be lambda upon 4 pi epsilon naught t raised to minus 3 by 2, and 1 by 2 let's take out, integration from d square to infinity. So x raised to n, integral of this is x raised to n plus 1 by n plus 1. So this would be t raised to minus half by minus half. Range is from d square to infinity, 1 upon 8 pi epsilon naught. So this would be equal to, if we put infinity it's 0, if we put d square it would be 2d. So this is not equal to 2d, this is 2 by d, because this is minus half, not half. Okay, so basically x component of electric field at yeah, that's why like this happens with questions which have a bit of calculation, you have to be very careful, which implies electric field at height of y is 1 upon 4 pi epsilon naught y. So this changes, electric field at height of x is 1 upon 4 pi epsilon naught x. So x cancels out, pi cancels out, so answer would be simply r by 2 epsilon naught. So the answer is very simple, the question is not. It's a bit lengthy question. Try to do every step on your own from the very basics, and if you get stuck at any point, pause the video, rewind it and see again. And this is not 1, this is lambda. See, so many mistakes. So this is here lambda, so this will be lambda r by 2 epsilon naught. Sorry for the mistakes, I do not want to re-record this video, but I think you understood the gist of the question. So now let's move to the next question. So this is an interesting one. So you are given large metal plates. So again, a bell should ring whenever you hear metal. Metal means conducting, and anything conducting, the property, remember the property, if there is anything conducting, the field cannot, electric field inside it should be 0. So in this electric field inside this plate should be 0. Here should be electric field should be 0. Here also electric field should be 0. Here also electric field should be 0. And large, whenever question says large, assume infinity. That's the way they write the question, but for our purposes we have to assume infinity. Okay, so we are given 3 plates and we are given net charge on these 3 plates. So net charge on the first plate is q, net charge on the second plate is 0, and net charge on the third plate is minus 2q. And what we have to do is we have to find charges on all the outer surfaces of all the plates. So we have to find charge on this surface, this surface, this surface, this surface, this surface, and this surface. There were 6 surfaces, we have to find charge on all the 6 surfaces. So the only trick is, as I already told, that assume an imaginary, imaginary Gaussian closed surface passing through these two plates like this. Now we know that electric field would be either in this direction or in this direction. So electric field through this and this would be 0. Electric flux through this and this would be 0. But we know that the electric field inside the conductor is 0. So here electric field is 0. Therefore electric flux through this side and this side, this plane basically, through this plane and this plane should also be 0. Similarly, this plane which you can't see, this plane of this, imaginary cubed, it's also parallel to the electric field. So flux through this should also be 0. So basically, in conclusion, the net flux through this is 0. So net flux through this is 0. So this is imaginary closed surface 1, imaginary closed surface 1. So if the net flux through this is 0, which means the net charge enclosed should be also 0. Flux net through imaginary closed surface 1 is 0, which is equal to Q enclosed by epsilon naught. So which means that the charge enclosed in this imaginary closed surface should also be 0, which means that if a charge of amount, let's say x, accumulates here, then a charge on this side of this metal, on this surface of this metal, on the right surface of this metal, then an equal and opposite charge should accumulate here, minus x, on this surface of the metal. And since the net charge on this metal plate is 0, which we are given in the question, so to keep the net charge 0, a plus x charge would be gathered on this side of this plate. And by the same principle, since the electric flux through this second imaginary closed surface is 0, which means charge enclosed should be 0. So to keep the charge enclosed to be 0, a charge of minus x would be accumulated here. I'm showing charge with plus sign, but it can be a positive charge or negative charge, we don't know yet. So it's just some charge. So x can be positive and x can be negative also, so we don't know yet. We are just saying that the charges would be equal and opposite. Whenever there are like plates like this, inside the charges would be equal and opposite. And since the net charge on this plate is Q, therefore the charge accumulated on this side should be Q minus x, because net charge should remain Q. And similarly, since net charge on this plate is 2Q, the charge accumulated on this side should be minus 2Q plus x, so that the sum of this and sum of this should remain minus 2Q, which is given in the question. So we have calculated the surface charge on the surfaces in terms of x, and if we find x, we can find charge on every surface in this question. So the only trick left is how to find x. To find the x, we will again use the same property, that electric field inside all of these is 0, and you can pick any of these, you will get the same answer. So I am picking this. So I am picking this point A. Electric field at this point A should be 0. Now to calculate the electric field at point A, we will use the formula, like we have an infinite surface with charge density sigma, which we derived in the previous lecture. If charge density is sigma, then at any point R, the electric field is sigma by 2 epsilon naught, which is independent of R. So it does not depend on the distance. So we can assume that in this question we have 6 infinite large plates. 1, 2, 3, 4, 5, 6. So electric field, and we can assume that all the charges on these 6 surfaces is positive. Like for the calculation purposes, we can assume that, we don't know yet, but if we assume that, we will get the right answer. So we can assume that, so the electric field at point A due to sheet 1 would be in the right direction. Electric field at point A due to sheet 2, 3, 4, 5, 6 would be in the left direction. And since the net electric field is 0, therefore electric field at A due to sheet 1 should be equal to electric field at A due to sheet 2 plus electric field at A due to sheet 3 plus EA4 plus EA5 plus EA6. So that net electric field at point A is 0. So this is like vector sum of electric fields, because electric field is nothing but a force. So electric field due to first sheet is sigma by 2 epsilon naught, and sigma is charge per unit area. Let's assume that it won't matter. Let's assume that charge of every sheet is A. It won't matter, it will cancel out, it won't matter. You can assume even a area to be 1 meter square. You can assume that for easier calculation, but let's assume it to be A. Then sigma is Q minus X by A, basically charge per unit area. So Q minus X by A is sigma by 2 epsilon naught is equal to the charge on sheet 2 is X, so X by A by 2 epsilon naught. Charge on sheet 3 is minus X by A by 2 epsilon naught. Charge on sheet 4 is X by A by 2 epsilon naught. You can see that 2 epsilon naught will cancel out, A will cancel out. For 5, minus X by A by 2 epsilon naught. And for 6, it's minus 2Q plus X by A by 2 epsilon naught. So 2 epsilon naught will cancel out, A will cancel out. That's why I was saying A won't matter. Only the charges would remain in the equation. So Q minus X should be equal to X minus X plus X minus X plus minus 2Q plus X. So this also cancels out. So the equation finally becomes 3Q is equal to 2X, and we get X is equal to 3Q by 2. Once you get X, you can find the net charge on every surface. So net charge on second surface is simply X, which is 3Q by 2. On this surface is minus 3Q by 2. On this is 3Q by 2. And on this is minus 3Q by 2. Here it would be Q minus 3Q by 2, which equal to minus Q by 2. Right? So here it would be minus 2Q plus 3Q by 2, which is also equal to minus Q by 2. Okay. So that's the solution for this question. Now let's move to our next and final question of this video, which is this question 10. So this was an advanced level question. This is also kind of an advanced level question. So you are given an insulating sphere, so it's not conducting, take care, and it has a cavity, and the question is in terms of vectors. So if your vector calculus is not strong, you might face some problem. Now what you have to do is you have to find the field inside this. So this is a cavity, and this is like solid sphere, insulating solid sphere. All this is insulating solid sphere, and this is a cavity. You have to find the field inside this cavity at point R vector. So let's say this point is R denoted by R vector. Okay. So if this point is denoted by R vector, then this vector would be R vector minus A vector. So please skip this question if your vector calculus is not strong. So now we have to find field at this point inside the cavity A. So to calculate the field, we will assume that there was a full sphere of, let's say this big sphere is of radius R. We'll assume that there was a full sphere of radius R, and then we will superimpose this with a negative small sphere of equal charge density sigma but negative. So this has charge density of rho, and this has charge density of minus rho. So we'll assume that these two spheres superimpose, and we will calculate the field due to this sphere. We'll calculate the field due to this sphere, which will give us total field at this point A. So basically we put this sphere here, and we calculate the field due to both of these spheres, and which will give us the field at point A. So inside an insulating sphere, the formula is rho R by 3 epsilon naught. Okay, so this formula can be simply converted into vector as rho r by 3 epsilon naught, because the direction, the magnitude of this vector would be rho r by 3 epsilon naught and direction would be radially outwards. So basically in vector notation, this is the field. So let's do part A. If you are not able to understand the question so far, please feel free to skip it. So for the part A, electric field due to big sphere is rho r by 3 epsilon naught, where r vector is shown in the figure. Electric field due to small sphere. Now for the small sphere also, the point is inside the small sphere. So, but for the small sphere, the point A has r vector as r vector minus a vector. And now we will add these. So net field at inside point would be rho by 3 epsilon naught into 2r minus a vector. Now for part B, we will take a point which is not inside the cavity, outside the cavity, but inside the bigger sphere. Let's say that point was this r vector, point B, and again this vector would be r vector minus a vector. So electric field due to big sphere, for big sphere the point is still inside, so it's simply rho r by 3 epsilon naught. For small sphere the point is outside. Oh, sorry, I did some mistake here. So it's minus rho, because the charge density is minus rho, so you have to take care. So it simply becomes rho a by 3 epsilon naught. That's the net answer. So just take care, I just realized. So here also you have to take minus rho and r vector. Now first check the formula for the point outside the sphere. For the small sphere, this point is outside the sphere. So since I'm teaching physics after a long time, I gave JEE. I don't remember these, but you should. So this is the formula, rho r cube by 3 epsilon naught r square. And this can be written in form of vector like this. Basically rho r cube r vector. Since the magnitude of r vector is small r, we have to divide by r also. So basically this becomes r cap, just to give the direction, by 3 epsilon naught r square. So this will become rho r cube r vector by 3 epsilon naught r cube. Okay, so let's go back. So rho 3 epsilon naught r cube. R cube means magnitude of r vector minus a vector cube, and capital R for the small sphere is just the radius of the small sphere. Are we given the radius of the small sphere? We should be given. So I am just writing this for now. I'll check the question. So this cube into the vector r vector minus a vector. So radius of small sphere is given to be b, so it would be minus rho b cube r vector minus a vector by 3 epsilon naught r minus a cube. And you just have to add this. And I don't think it is any good way to add this. You just add this to get your final answer. So yeah, so this is also one of the difficult questions. The last three questions I would say were difficult, advanced level, this you can say means level, and then we have CBSE level. So I have covered a good depth and breadth of questions, and I hope that after going through these questions, it would be easier for you to tackle any type of questions based on Gauss law or electric flux. If you like this video, stay tuned. Bye bye.